So this is problem number 6 from the 2012 AP Calculus AB free response set. And this is a non-calculator problem, and it's probably what makes this problem challenging. You have to do some uncomfortable things without a calculator here. But what you have is you have a particle that's moving along the x-axis. You know the velocity is going to be given by this function, and then the initial position of the particle is at x equals -2 when t is equal to 0. Part A asks us to determine when the particle is moving to the left. Well, motion is to the left if velocity is negative. So when is velocity less than 0? Then our motion is going to be to the left. So we have to determine the answer to this question right here. When is cosine of pi by 6 over t less than 0? So what I did to answer this was I drew myself a unit circle. And I know that the x-coordinate at any point on the unit circle is going to correspond to the cosine of that angle. And I realized my x-coordinates are positive in these two quadrants, so cosine was positive in those two quadrants, and then my x-coordinates are negative over in these two quadrants, so cosine is going to be negative in these two quadrants. The next trick is trying to figure out what value of t leaves you within the second and third quadrants here. And so what I did was I realized at this angle right here, that would correspond to an angle of pi by 2. So I set the quantity within my cosine function equal to pi by 2, and I solved that for t, and I got t equals 3. So t equals 3 puts us right here on the unit circle, and then as we progress around the unit circle, we go over into the fourth quadrant as we cross the angle of 3 pi by 2. So I also wanted to figure out when cosine was equal to 3 pi by 2, or when the expression within the cosine function was equal to 3 pi by 2. So I took that expression, set it equal to 3 pi by 2, solved for t, got 9. So as t ranges from 3 to 9, the angle, or the value within the cosine function here, is going to range between pi by 2 and 3 pi by 2, and we're going to end up with a negative value for velocity. So motion is to the left as t ranges between 3 and 9. Part B should be very simple. There's not a lot to it. They don't really ask us to evaluate anything. They want us to write an integral expression that gives the total distance traveled by the particle from 0 to 6. So if we just wanted to know how much position has changed, we would just integrate velocity. But we know velocity can be positive, velocity can be negative. So if we have motion in the positive direction and motion in the negative direction for a certain interval, and we definitely do here because we said in part A that motion was going to be to the left from 3 to 6, but it's actually going to be to the right from 0 to 3. So we wouldn't want to do this with a single integral without any absolute values, but as long as we put absolute values around our velocity and change the sign of any negative velocities to a positive velocity and integrate, we're going to have total distance traveled. Without the absolute values in here, this doesn't give total distance traveled any longer. It would actually give the change in position from 0 to 6. So here was your expression for total distance traveled. Another way you could have done this is you could have done the integral from 0 to 3 of v of t and then minus the integral from 3 to 6 of v of t, only because, well, v was going to be negative from 0 to 6. You'd end up with a negative value for the change in position, and if you subtract the negative, it's just like adding. Either way you get this. The far simpler expression to use would be what I have on the screen here. As we move into part C, we wanted to determine the acceleration function for this particle. So you just have to recognize that acceleration is the rate of change of velocity, or the derivative of velocity. So taking the derivative of this velocity function using the chain rule is going to give us this. So the derivative of cosine is negative sine. We leave the inner function there, and then times the derivative of the inner function. We want to find the acceleration at 4 now. So the acceleration at 4 is going to be this value. And the reason why we need to know this value is because we want to know if the speed of the particle is increasing, decreasing, or neither at t equals 4. Well, sine of 2 pi by 3 is going to correspond to the y-coordinate on the unit circle at this angle of 2 pi by 3. So pi by 3 would be 60 degrees, go another 60 degrees around the unit circle, and this would give you 2 pi by 3. The y-coordinate at this point is positive. So this expression right here, sine of 2 pi by 3, is going to be greater than 0. That's going to imply that the acceleration at 4 is negative, because you have a negative value here times a positive value here. So acceleration is negative, and from part A we determined that velocity was going to be negative from 3 to 9, and so acceleration is negative, velocity is negative. If you think about what this tells you about the velocity graph at 4, your velocity is negative, so I have a point below the x-axis or the t-axis on my velocity graph, and if I draw my velocity in, since acceleration is also negative, I have to have a negatively sloped tangent line. If you look at what's happening with velocity on this little interval, velocity is moving away from 0. And since velocity is moving away from 0, and speed is the absolute value of velocity, speed would actually be increasing. We have a more and more negative velocity as we go through this little stretch of the velocity graph, and because of that, speed is increasing. And then the last part of this, part D, wants us to find the position of the particle at t equals 4. So the position of the particle at t equals 4 is going to have to take into account where we started at a position of -2, plus how much the position has changed from 0 to 4. So if we integrate the rate of change of position, which velocity is, from 0 to 4, we're going to have our result. You have to do a u substitution here, so you let u equal the inner function, and you pick up this ugly sort of constant here whenever you go through the steps to figure out what to replace dt with. When you do the substitution, just make sure if you are leaving these as 0 and 4, you recognize that they are t values, they are not u values. So I just have my little reminder here that these are t values. I can't accidentally put them in place of a u. But then if I factor this constant out in front of the integral, and then take the antiderivative of cosine, I get sine. I would need to evaluate this from 0 up to 4, but again, those are t values. So we'll go and put this expression back in place of u before evaluating. And then when you evaluate, it comes down to trying to figure out what sine of 2 pi by 3 is, and then minus sine of 0. Sine of 0 is 0, and then if you use your left-hand trick to figure out the y coordinate on the unit circle at this point, you're going to end up with square root of 3 over 2 for the sine of pi by 3. And that's also going to correspond to the sine of 2 pi by 3, since the y coordinate would be the same at either of these points on the little unit circle I've drawn over in the left corner of the screen here. If you continue to try to simplify, you can divide both of these by 2, or basically just cancel them, and then you're left with a 3 outside the root. You still have the square root of 3, and it's over pi. So kind of an ugly expression, but that is going to be the final position at 4 for this particular particle.